Students, welcome to my second video of my special topics lecture series reviewing chapters 6, 7, and 8 from the first semester of general chemistry. In this one, we're going to begin by learning about quantum numbers, or I should say relearning about quantum numbers. Are you guys ready? Let's go ahead and get into it. So, each electron in an atom can be described by using four different numbers called quantum numbers. These numbers are kind of like an electron's address. I'll now describe each of these four numbers. The first one is called the n, or principal quantum number. This number can be any integer, 1, 2, 3, 4, etc., and describes how far an electron is away from an atom's nucleus. For example, an electron in a 1s orbital has a principal quantum number, or n number, of 1. An electron in a 3s orbital has a principal quantum number, or n number, of 3. An electron in a 3p orbital has a principal quantum number, or n number, of 3. An electron in a 4d orbital has a principal quantum number, or n number, of 4, and so on. The higher the n value, the higher the electron is in energy, and the further away it is from the nucleus. You can see in this picture that the only difference between a 1s, a 2s, and a 3s orbitals, and by extension a 4s, 5s, 6s, and so forth, is their size. All of them are spherically shaped. Now, the next quantum number is the L, or azimuthal quantum number. This number describes what kind of orbital, either s, p, d, or f, the electron is located in. An electron in an s orbital has an L value of 0. An electron in a p orbital has an L value of 1. An electron in a d orbital has an L value of 2. And an electron in an f orbital has an L value of 3, as I've summarized right here. So please make sure that you memorize that if L is 0, the orbital you're talking about is an s. If it's 1, the orbital you're talking about is a p. If it's a 2, the orbital you're talking about is a d. And if it's a 3, then the orbital you're talking about is an f. The next quantum number is the m sub L, or magnetic quantum number. This number can be any integer from negative L to positive L, including 0. The magnetic quantum number m sub L describes the orbital's three-dimensional orientation in space. For example, you should remember from our previous slide that the L quantum number for p orbitals is 1. This means that the m sub L number for all p orbitals can be negative 1, 0, or positive 1. And what does that mean? Well, these three numbers, negative 1, 0, and positive 1, represent the three different kinds of p orbitals, one along the x-axis, one along the y-axis, and one along the z-axis, as you can see in these pictures. So once again, all sets of p orbitals have three lobes or dumbbells, one straddling the x, one straddling the y, and one straddling the z-axes. If I've got an L subnumber, that is an azimuthal quantum number of 1, that tells me I'm talking about a p orbital. But what kind of p orbital? Am I talking about the one along the x, the y, or the z? Once again, that is the m sub L number. If it's negative 1, it may correspond to z. If it's 0, it may correspond to x. And if it's positive 1, it may correspond to y. Honestly, since these are all perpendicular to each other and are essentially equivalent, I don't really know if one specific number refers to one axis and another to another. But anyway, you sort of hopefully get the idea. Now, the next quantum number is the m sub s, or spin number. The spin number is the last quantum number and is equal always to plus or minus 1/2. That is, for any two electrons occupying the same orbital, one is assigned a positive 1/2 spin and the other is a negative 1/2 spin. Let me explain further. If, for example, two electrons had identical quantum numbers n, L, and m sub L, then that would mean that they were in the exact same orbital. But no two electrons can have the exact same four quantum numbers in the same atom. So what would we do? Well, we would assign one electron a plus 1/2 spin and the other a negative 1/2 spin. This would mean that these two electrons, both shooting inside the same exact orbital, are revolving around their individual axes in opposite directions from each other, like this. As I mentioned, the Pauli exclusion principle says that no two electrons in the same orbital in the same atom can have the exact same four quantum numbers, n, L, m sub L, and m sub s. Does that make sense? I hope so. So in summary, there are four different quantum numbers which we can assign to electrons and which function kind of like an electron's address. The first one is n, or the principal quantum number. This number can be any integer starting with 1 and tells us how far away an electron is from that atom's nucleus. The larger the n number, the further away that electron is, and the higher in energy and more reactive it is. The second one is the L, or azimuthal quantum number. It is always equal to 0 for s orbitals, 1 for p orbitals, 2 for d orbitals, and 3 for f orbitals. And those are the only 4 options you have for the azimuthal quantum number. Third is the m sub L, or magnetic quantum number. This is equal to all integer values from negative L to positive L, including 0. This describes the orbital's orientation, or which kind of that type of orbital we're talking about. For example, if I've got a p orbital, it has an L number of 1, which means that it can have an m sub L number of +1, 0, or -1. Each of those 3 numbers, +1, 0, and -1, corresponds to a different orientation of a p orbital around the nucleus. One straddling the x-axis, one straddling the y-axis, and another straddling the z-axis. What if you have an azimuthal, or L number, of 0? Well, that corresponds to an s orbital. What numbers of m sub L can you possibly have for that? Well, you can have +0, -0, and 0, which are essentially all just 0. That's the only options you can have. So for s orbitals, there exists only one orientation around the nucleus. S orbitals are shaped like a sphere, and you'll notice that if you rotate them around that axis so that they're straddling the x, y, or z axes in different ways, it still looks exactly the same, because it's totally just a sphere. So s orbitals are kind of boring in their quantum number world, at least, because all they have for their m sub L, or magnetic quantum number, is also 0. The last number is the m sub S, or spin number. This is always going to be equal to +1/2 or -1/2 if you've got 2 electrons occupying the same orbital in the same atom. Now, table 6.2 from our text summarizes this stuff all pretty well, I think. And that brings us then to a couple of quantum number questions. Which one of the following represents an acceptable set of quantum numbers for an electron in a 2p subshell? Now, I'm not going to answer this question for you, but we'll post a link here to a separate video in which I answer some similar questions that you're welcome to watch for some help. Here's another one. Which one of the following represents an acceptable set of quantum numbers for an electron in an atom? Okay, it's essentially the same question with different sets of numbers. Once again, I'm totally not answering this for you here, but we'll post a link to a separate video in which you can watch me do some similar problems to help guide you if you like. And here's another one. It's essentially the same question. Which of the following represents an acceptable possible set of quantum numbers for an electron in an atom? Much the same. I'm not answering it here, but we'll leave this link up here for you to consult if you'd like to for help. That takes us to the end of this video. Please stay tuned to the next one, in which I'll begin teaching you ionization energies and periodic trends in the periodic table. Until next time, my wonderful students, I beg you to have an enjoyable rest of your day.